recording. Okay, so today we're doing half of chapter 12, constrained programming, which is awesome given what I already read, but it feels a little bit too magical. Uh, but well, we haven't read all of it yet, so maybe my questions will be answered. So a constraint is simply a logical relation, such that x is less than y, or y is a multiple of 3. And essentially, this constraint satisfaction problem can be solved using brute force, but our goal will be to try to reduce the amount of search space uh, required to find a solution. Um, for many problems, the search cannot be entirely eliminated. Solving CSPs is related to deep questions of intractability. Problems that are known to be intractable will always need some search. And then, how are we going to solve that? So this feels pretty related to logic programming and relational programming. We're gonna.
Yeah, this is like a bit of a generalization. You can think of relational programming as being um, a variant of constraint programming where the only constraint you have available is equality, right?
Well, not only that, but there's also the absence of local deductions, right? Relational programming only uses the constraints that you, the programmer, establish. It doesn't create new ones based on the local understanding.
Um,
Which,
Kinda. I mean,
to me, kind of means that relational programming is a dumb version of constraint programming.
yeah, this is basically like it's a natural way to generalize it because you want to be able to deal with partial information in more ways than just, oh, this variable is instantiated or not, you know?
Yeah, speaking of partial information, um, well, these are three important ideas to keep in mind. So partial information, so we may not know the solution, but we may discover partial truths to the problem. So we're going to call this partial information. Local deduction, which to me is the magic. Like I'm really curious to know how this is implemented under the hood because it seems very magical. For example, if we have x is less than y and x is greater than 100, we can deduce that y is greater than 101. And if you think about it, this conclusion is true given these two other things, but how is this being solved in a programming like mechanically?
Um, for numbers in particular, the canonical way to do this is you use intervals instead of concrete numbers.
Yeah, but that's a very simple, naive case. What if you have more complicated sentences? So that's what I'm curious to know about and probably gonna know next time, next session. And then we have controlled search. When no more local deductions can be done, then we have to search. The idea is to search as little as possible. We will do just a small search step and then we will try to do local deduction again. A search step consists of in splitting a CSPP into two new problems. One considering C and the other one negating C, in which C is a new constraint. Since each new problem has an additional constraint, it can do new local deductions. To find the solutions of P, it is enough to take the union of the solutions to the two new problems. The choice of C is extremely important. A well-chosen C can lead to a solution in just a few search steps. So this is probably another thing to keep in mind. There is some sort of it's the same thing as the merge sort thing that Marinho explained in the relational program. If you want to sort
Yeah,
an array, you can just ask for it to be sorted, or you can structure it in a way that you can lead to the solution being merge sort naturally. This also has the same property of like the you cannot ask for a miracle naively.
Yeah, normally with constraint problems, you want to incorporate domain knowledge to avoid expensive search, usually.
I would go even further than that. I think it's an understatement what you said. It's not only domain knowledge, it's maybe a non-trivial particular property that can be exploited to make it faster. And the best example of this is the palindrome problem of being multiple of 11. I wouldn't say that's a trivial conclusion, but that's definitely true. And if you can put that in there, you can speed things up really fast. But that's the thing. Somebody needs to get the the eureka moment of like, hey, we can actually say it's multiple of 11, and then that's it.
Yep.
Okay, so let's say so calculating with partial information. So we're going to use integers as our example, calculating the area of a rectangular field. So we know that x is between these two numbers and y is between these two numbers. In OS, we describe this information like this. So they have even special syntax for that. Um, then we also say that we know that the multiplication of both of them is greater than 4,000. So we say that hey, the area A is between 0 and 10,000. A is also the result of the multiplication of these two things. And then give me, is this true? Yes, actually. Uh, and the answer is going to be yes, because the minimum amount of area that you need there is 4320. And the reason is that is because if you pick the two least possible values of x and y, which is 90 and 48, that's going to lead you to 4320. Uh, Technically, it's called a propagator. So these things, they're not called predicates, they are called propagators.
Yeah, you can encode predicates as propagators, but a propagator does something that a normal predicate in a relational language doesn't do, which is if you give it more detail, like if you add more data to your partial information, the propagator will run again to further constrain its outputs.
Yeah. Um, in this case, the propagation is simple. A minimal value of a is updated to 90 times 48, and the maximum value is 110 times 53. Note that we have to give the initial information about a, for example, that is an integer between 0 and 10,000. If we don't give this information, the constraint multiplication a times this will block. Which leads me to my first question. Why would that block?
Why would that block?
If I'm already
Um,
establishing that a is equal to the multiplication of these two values, and I'm asking if a is greater than 4,000, this first information is irrelevant to the question.
this might be a limitation of Oz specifically. I know there are propagation systems in based on scheme. There's that talk from Gerald Sussman that I linked a while back. Actually, I think it's been over a year now, actually.
Mm-hmm.
Um, where in that system you actually don't need to do this. You just need to say, okay, A is a fresh propagation variable, and then you say X is in this interval, Y is this interval, and then I apply the multiplication propagator to X, Y, and A, with A being the quote unquote output, right?
Yeah. Okay, so we're gonna just say that this is a limitation on loss. Now let's add some more information about x and y and see what we can get from there. Let's say that we know that the difference between x and 2y is exactly 11 meters. So this is in the way that this problem is structured. We are creating a system of equations. Now we have this one equals to 11. We know that one times the other is um, at least this number and less than this number. So we're essentially creating a system of equation. This is the equation in this case. This new constraint is also a propagator. It does a local deduction with the information we know about the x and y. The browser displays automatically updated to this thing. This considerably increases the accuracy of our measurement. We know that the area must be from between these two numbers. What do we know about x and y? Yeah, so we are further restraining the possible values of x and y. So this is pretty awesome. I just want to know exactly what is the engine that is like going through the propagators to generate these extra conclusions. Because to me that's really sounds magical. Like this example with only integers is fine because there's like just use intervals, that's okay.
Mm.
But what about the general case?
Uh, okay, like propagators are actually deeply related to reactive programming. Well, in this case, FRP, except this is bidirectional, right?
Mm-hmm.
When you make a propagator, like connecting two or more variables, propagation variables, let's use that term because it's nicer. When you make a propagator constraining two or more propagation variables, it will look at each of them, and if any of them gets additional information, um, it needs to run basically a different mode to push that information to the other variables to further constrain them based on the new input. So
So
like you
it
know
is
how in
FRP.
ah kinda kinda well it's not quite because as I said the information here can flow in both directions, right?
That doesn't that doesn't I don't know why that puts a limitation on FRP definition.
Because in FRP, if you say, okay, the information can flow both ways, that's kind of like sending information backwards in time, no?
Well, it, that is going to the nitty gritty of things because in the case of FRP, the R stands for reactive in terms of time. But in this particular case, we're not using time as a measurement. We're using adding new information, whatever that means. We
Well,
react
yeah.
to the addition of information, not to the pass of time.
Well, yes. I guess in that case, you could call this a reactive system, yes, because each time you add new data, like each time you constrain any of the variables in the system in some way, whatever propagators are connected to that variable will push that information outwards by further constraining the other variable it is constrained to. And that may cause other propagators to fire, you see?
Yeah. So it has an FRP aspect, but the reactive is not to the passage of time, but is actually to the addition of new information. Cool.
Basically, yeah, yeah. This is a system that keeps accreting information either until it stabilizes or until it reaches a contradiction, in which case, yeah, it stabilizes on failure in that situation.
Okay, so now another example. How can I make a rectangle out of 24 unit squares so that the perimeter is exactly 20? These can very easily be encoded into a system of equations. Uh, there is also this third equation here that one is strictly less than or equal to y. Um, the third equation is unnecessary strictly speaking, but including does no harm. It will make the problem solution easier. These three equations are constraints. We call this equation propagators since we use them to make local deductions, propagate partial information about a solution. To solve the problem, it is useful to start with some information about the variables. We bound the possible values of the variables. This is not absolutely necessary, but is almost always possible, and is often makes solving the problem easier. For our example, assume that x and y each range from 1 and 9. This is reasonable since they are positive and less than 10. So we know that x plus y is equal to 10 because of this equation. So that means that, and because this is an area thing, so they are both positive, and their sum is equal to 10, so we can assume that both of them is between a 1 and 9. So this creates these two extra pieces of information. We call these equations basic constraints since they are of this simple form variable in an explicit set. And then we start the mechanical process, which I still don't know how this is being done in a programming manner, but in terms of intuition, makes a lot of sense. So we have three propagators. We know that x times y is equal to 24. We know that x plus y is equal to 10, and then x is less than or equal to y. We are adding this new piece of information. What is on the right is a new piece of information. What is on the left is called the computation space S1. A computation space contains the propagators and the basic constraints on the problem variables. As in the previous example, we use this notation. We have three propagators. Syntactically, we show that these are propagators by adding a column to their name. And now we do the local deductions, which is essentially smashing the computation space with the extra constraint and see what we get from there, what we can do with those two pieces of information. So for example, the propagator x times y equals 24 notices that since y is at most 9, then x cannot be 1 or 2. And why? Because if it's 1, if x was equal to 1, that means that y is 24, but we know that y is at most 9, so that cannot be true. If x was true, then y needs to be 12, but we also know it needs to be capped at 9, so that also cannot be true. So then, by just using simple math, we discover that the new interval needs to be with x starting at least with 3. And it follows that y is at most 8. The same reason can be done with the roles reversed. And then the propagator therefore updates the computation space. So then we go from this thing to this thing. Now the propagator x plus y enters the picture. It notices that y cannot be true, therefore x cannot be 8. Why is that? Because y being true and then sum being 10 means that x would need to be 8.
Mm, that would be valid, but the reason that cannot be is because, well, x is at least 3, right?
Oh yeah, we are doing like a couple of implications here. Y cannot be true because if that was true, then this would be wrong.
Yeah,
Which
because
means
if
by
y is,
necessity that x is not 8.
yeah, if y is 2, then it follows that it cannot be, actually it can't be 2 because it will be smaller than 3, which is the minimum value for x, and we have the constraint that x is at least equal to, well, y is at least equal to x, right?
Well, you can also use that line of reasoning. I don't think that's the one being used in here. I think what is being used here is that if y was true because of this equation here, x would have to be 8, but y cannot be true because it needs to be at least 3.
So x
Hence,
cannot be 8, yeah, it
exactly,
needs to be at most 7.
exactly. So then we like the funnel keeps like we are filtering more things. And then the propagator x times y equals 24 can do more deduction. Since x is at most 7, which is written here, therefore y must be at least 4. Because 3 times 7 is definitely less than 24. And why is that? It's because uh, if y was 3 and we know that x must be at least 7, 3 times 7 is 21, which is definitely less than 24. So there's that. If y is at least 4, then x must be at most 6. So then we can refine this even further. At this point, none of the propagators see any opportunities for adding information. We say that the computation space has become stable. Local deduction cannot add any more information. And then we have to make the guess. Let's say that x is equal to 4. To make sure that we do not lose any solutions, we need two computation spaces. One in which x is 4 and another in which x is different than 4. This gives S2 and S3. So this is the one that we say that x is equal to 4. Well, immediately at first glance when I read this, I was like, this is wrong. Because if x is equal to 4, y cannot be a range because of
Well,
this.
this is immediately after we added this new fact, so none of the propagators have any chance to run yet. So y
Yeah,
is
but
still an interval because of that.
yeah, to me it could be just to this because it's also being called S2. So to me this is just making confusion out of nowhere. But okay.
Well,
Uh,
no, it's because well, propagators, the propagation cells, their propagation variables, they are mutable, but they are monotonically increasing the amount of information that they contain.
sure, sure.
So when you say, okay, x is equal to 4 now, but none of the propagators had any chance to run, then y will still be an interval because for y to not be an interval, some propagator must have noticed that, okay, x is 4, and then probably the plus propagator actually would say, okay, if x is 4, then y must be 6 because they add up to 10. Like the output is a constant.
Yeah, the way that I imagine this running is that you have your S2 and then you call a function or a procedure saying that x is equal to 4 and the output is the new computation space which already has y pinned to 6. So to me this transient state only makes sense like on paper. I don't know how in the implementation we'll handle this particular state explicitly. But you're right. Like in a technical sense, the propagators haven't been running; they are stopped. So then you have to press a button, and then they will go to this. I just think that we could just already went to this. And then S3 is the opposite, right? Because we ended up with the interval being between 4 and 6. If we're saying that x is equal to 4 and the other one is not equals to 4, that necessarily means it's between 5 and 6, um, which is okay. Each of these computation spaces now has this opportunity to do local deduction, so run the propagators. So after we do that, S2 becomes this, obviously. At this point, each of the three propagators notices that it's completely solved. It can never add any more information, and therefore removes itself from the computation space. We'll say that the propagators are entailed. This gives, boom. The result is a solved computation space. It contains a solution x4, y6. Let's see what happens with S3. Propagator x times y equals 24 deduces that x is equal to 6 and y is equal to 4. Is the only possibility consistent with itself. Then the propagator x is less than or equal to y sees that there is no possible solution consistent with itself. So then it fails. Which probably means that we are killing this subtree.
Yeah, the S3 subtree dies because it reaches an inconsistent state, so it says, I failed,
Yeah, and
basically.
then we conclude that x is equal to 4 and y is equal to 6. But I would like to point that out that this is kind of how should I say this? It
Yeah,
is
this is just
harmful.
cutting
It is
this.
harmful because it's saying here that it was harmless to add this inequality, but we just saw that there was a side effect of adding such because nothing from the original problem forbids x being 6 and y being 4.
I mean, that's just a symmetric solution. Symmetric by rotation, I mean, right?
Yeah, but this is a simple example. Imagine that you add an arbitrary thing like this and there are like huge consequences, huge side
I
effects
mean,
from doing so.
yeah, that kind of varies by problem. In this case, there's the rotation symmetry, so it doesn't matter, but in general, you should be really careful about adding constraints to reduce the search space because you may inadvertently forbid a solution that would otherwise be
Exactly.
valid.
Exactly. So even though this is fine, I would like to point out that if removing the arbitrary third inequality, then x being equal to 6 and 4 equals to y equals to 4 also solves this particular problem here. Um, Executing the example. Okay, so now we go to the DSL required to run this, which again, I'm very surprised that they use very dedicated syntax for this. Because in the relational program, there was a way to interact between the quote unquote normal programming and the relational programming. And they could like interchange. Well, we're still doing that because this is all wrapped in a procedure.
Well, yes.
But this has like the double column syntax and stuff like that.
The text will mention this later, but this is not the same as just declaring a variable to be equal to something because, first of all, this is an interval, not just a number, which would be fine because if you pay attention to the syntax, you see that this is just a pair, right?
Yeah, but I'm very surprised
Internally.
that instead of using functions or procedures to encode this, or records even, given that they
You,
already used this before, they decided to create special syntax for it.
I mean, this is, you would need some, you would not be able to use the standard syntax regardless because you need something that is, you need a store of information that allows the collected information to increase in a consistent manner. So it needs to be something that is mutable, but allows you to get an immutable reading of the current information set. Um, and all of the propagators, they actually need to spawn a thread to keep watch over each of those cells so they can update it whenever new information is added into the system.
That is fine. Nothing what you said is in conflict with what I said. What I said is that instead of creating, I don't know, x equals to interval record open parentheses 1 comma 9, they decided to create special syntax for that instead of just leveraging the records and the tuples they already have.
But they are. This one
They
hash
are
9 is just a pair.
sort of because
The
this is a
operator is
pair.
weird.
This is definitely dedicated.
No, it's just a colon colon. It's kind of like equality, but it's not equality because you're not saying this is strictly equal to that. You're saying this is consistent with that,
No, no,
right?
no, no. The column has a special meaning. I think we already read that.
Oh yes, but that's because those are not the standard operators of the language
Exactly,
that
and
we've seen so far.
that's my question. Instead of just using records and functions, I don't know, passing like you were gonna call distribute here anyway. Why just don't why not just put the list of data flow variables in there? Like, what's up with that?
Uh, well, this is not just a list of variables, right? You're also setting up all of the constraints, which if you wanted to use standard syntax, they would have to be procedures, but they would have to be different procedures from the normal arithmetic operations, right? This makes them look kind of similar to normal arithmetic.
I agree with the second part, which is that they are leveraging the familiarity that looks like it. That's okay. I still don't buy the first one, which is that we already went through the graphics chapter in which they abused the record system to be able to create a DSL dedicated to their purpose. Why they are not doing that in here? That's kind of my thing. Like I'm not
They
criticizing because this is
they
awesome, but
can't because records are immutable, Lemos.
that doesn't matter. Man, you were just creating a way to describe things. What you're doing with the data being held inside of them, you can do it whatever you want. If it's
No, no,
mutable
no,
or
no, no,
immutable, it doesn't matter.
no, no, no. It matters. They need to be mutable, Lemos.
You're not getting my point. You are calling a distribute function that can do whatever we want. We can do mutable stuff, you can do immutable stuff, it doesn't matter. The only thing that matters is a way to have a description of the things. That's the only thing that matters. Everything else can be done in whatever way we want. If it's mutable or immutable, I'm just talking about how you're describing the problem. Because after looking at the graphics chapter, I thought, like, okay, are they going to use the same trick as before? And they didn't. Your argument of the familiarity is a good one. I haven't thought of that. Maybe they do want this to look like arithmetic things. Okay. Uh, um, that was just like an observation that because after the graphics chapter I was like, man, okay, why are we creating new syntax then? What is the rationale between, okay, this deserves new syntax, this doesn't?
Well, I guess the familiarity here would be the main argument if you're just talking about the syntax, because otherwise you'd have to have an asterisk for normal multiplication, and then you would have like I don't know constraint multiplication, which would be a
Yeah,
procedure, right?
yeah. It would have more. It would be a noisier notation with more noise. Anyway, the solution is returned as a tuple sol, which contains the two variables x and y. Here we have the intervals and the multiplication and then the inequality propagators. fd.distribute call selects the distribution strategy, which we don't know what that is yet. The chosen strategy naive selects the first non-determined variable in sol and picks the leftmost element in the domain as a guess. To find the solutions, we pass the procedure to a general search engine. Solve all. This displays a list of all solutions, namely 4, 6, since there is only one. All the constraint operations used in the example, the operations with column, are predefined in a Mozart system. The full constraint programming support for Mozart consists of several dozen operations. All of those operations are defined in the constraint-based computation model. This model introduces just two new concepts to the stateful concurrent model: finite domain constraints and computational spaces. Okay, so let's go into more detail. The fundamental concept used to implement propagating search is a computation space which contains propagators and basic constraints. Solving a problem alternates two phases. A space first does local deductions with the propagators. When no more local deductions are possible, the space is stable. Then a search step is done. In this step, two copies of the space are first made. Wait. Hmm. I just kind of like a thought came to my mind of like, is it possible to do local deductions on the context of a database?
I don't see why not.
I do see why not. Because if you're doing the database modeling properly, you will not be able to deduce anything that is not already in the database. Am I wrong?
You would not be able to deduce anything that is not in the database.
Already. Because here's the thing. This local deduction thing is about finding new truths based on the truth that you already have. But on a database, if you're doing everything 100% properly, there that will not be a thing. Like you will not be able to create new truths that they are not already recorded by the database.
Hmm. I mean, I guess you would be able to use propagators only in the context of a query. They don't really make much sense in the context of, okay, let's just store the known facts.
Exactly. But you got it, right? That this makes sense to optimization of queries. But in terms of trying to deduce new data from the database, that that is only possible if you did something wrong, right?
I mean, I guess technically this could also be used for write transactions, like the whole thing of, okay, if you want to write on a view, for instance, right? You would probably have some kind of propagation network to map that view back to the actual stored data, right?
Yeah.
Um, and I'm pretty sure Magetta has been dealing with that in previously Domino, now Sakura, with regards to constraint enforcement, oddly enough.
Yeah, no, but he's using the provenance and the what's the other thing? Uh, heritage? I don't remember, but he has information of what are the original tables that came up to be combined to create a view. So he knows where to go back and like propagate the changes of the view into the original tables. Uh, but this is a very interesting thing. So this only makes sense for queries. This doesn't make sense for data.
Well, it makes sense for an active system where data is being added into the system. It doesn't really make sense for like a passive storage of knowledge, right?
What do you mean by active?
Because propagators are actually, well, we're going to see this in a moment, but a propagator, when you instantiate it, it becomes a thread
Yeah,
and it keeps constantly observing the variables it is connected to. And if any one of them receives new information, it runs its logic to update the remaining ones.
but that's what I'm saying. If you did everything on a database on a relational database correctly, as soon as the insert happens and the triggers are triggered and then the propagators came in, there's nothing else to deduce from that
Um,
insertion.
well, actually, the triggers in this context would be the closest thing to the propagation system.
But that I don't think so because the triggers need to be manually written. Propagators are mechanical.
Well, you have to. Somebody has to implement the propagators to begin with, no?
Um, okay, I have a question then.
Okay.
When we say that we provide this to the system and the system refines the interval to these other versions, these are still propagators.
Those are not propagators. The propagators are on the left, actually.
Oh, okay, so actually nothing that we do actually creates new propagators dynamically. We always only have the propagators that we start from the beginning.
I mean, you could have a propagator that generates other propagators if it's recursive, for instance. But most propagators are not recursive. So, yeah, typically, whatever set of propagators you instantiate at the beginning is what you get until the space stabilizes,
Ah, okay,
basically.
so in that case you're right. The triggers are the equivalent of these things. I thought these would still be called propagators though.
They
Or I was
aren't.
wrong.
They are just variables with partial information in them. By themselves, they don't propagate anything.
Oh, I thought they did, because when you say this and you propagate this information to this guy, there is a
No, no,
side
no. It's not
effect out
that.
of that.
No, 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 no. When you say x equals 4, the the propagator that you have highlighted here, the x plus y equals 10, is going to notice, oh, x got updated. I should see what that implies for y, which is the other variable I'm connected with. You see, the propagators are actually the equations, or rather, the threads enforcing those equations on the variables.
Okay, so these are only variables, even though they have columns in them. That's a very subtle distinction. Where are they defining the meaning of the column?
Well, those are just operators. It's just that by convention, those that have a colon are based on the constraint model, right?
Oh, so that's what it means. Doesn't mean you are a propagator. It means that you are using the constraint model. Okay.
Yeah.
Okay, so that's fine. Cool. Okay, anyway. A basic constraint C is then guessed according to the heuristic called distribution strategy. The constraint C is then added to the first copy, and negation of C is added to the second copy. We then continue with each copy. The process is continued until all spaces are either solved or failed. This gives us all solutions to the problem. Yeah, we haven't read what is a distribution strategy yet. And this is something that bothered me, that we only see the definition of that down here instead of the beginning. Now that we have seen the basic concepts, let's see how to program with them. A constraint problem is defined by a one-argument procedure. The procedure argument is bound to the solution of the problem. Inside the procedure, next to the usual language operations, two new kinds of operations are possible. Constraints, they specify the relationships between different parts of the problem. They can be either basic constraints or propagators. Specification of distribution strategy. This specifies how the search tree is to be formed, which constraint C and negation C are chosen at each node when doing a search step. So this is, now we are starting to understand what is a distribution strategy, which is the act of choosing which constraint we're going to do the bifurcation.
Yeah, it's basically you have a tree of possibilities, and the distribution strategy specifies, okay, how are we going to pick the branches that we're going down?
Yeah. In contrast to relational programming, there's no explicit creation of choice points. Yeah, because here's the thing. When you're doing relational programming, you had to specify that, okay, this is a choice, this is a choice, this is a choice. So all the subtree creation process we're doing manually by the programmer. In
Yeah,
this thing, the runtime system actually does that for you, uh, and you have just an API. You just put an
yeah,
atom here and let it fly.
yeah. Basically, in the relational model, you have to program all the ORs explicitly, but in the constraint model, the ORs are just implied by the constraints you chose.
Not by that, but by the distribution strategy.
No, the distribution strategy just tells you how you're going to traverse the tree of ORs. It doesn't tell you what the ORs are to begin with.
No, that's a search strategy, not distribution
We,
strategy.
well, a search strategy is just the distribution strategy for a relational program, which is a subset of
I don't think that's right, friend. Let's jump a few chapters here. I remember pretty explicitly that they are defining search strategy and distribution strategy very differently. So let's see.
I might be misremembering now that you mention it.
Yeah, but I'm not finding it
Oh,
though.
I saw it. Scroll down a little bit, just a little bit. I think it's in the next page.
No, no, but this is 12.4, which means I didn't read further from here.
Oh yeah, no, we're just
It's
going
it's
up to
def it's
12.3.
it's definitely up here. Okay, let's continue reading. Maybe I am the one misremembering as well. That's fine. It's just because I particularly remember that there is a paragraph that is specifying what is the search strategy, which is depth first and breadth first, and then there's the distribution strategy, which is how are we gonna choose the constraints to bifurcate. But let's continue going because maybe I misunderstood. It's also possible. So let's continue reading here. Now that we have the basic concepts, let's see how we can program with them. As example, we take the well-known combinatoric puzzle, send plus more equals money. I never heard of that. The problem is to assign digits to letters such that the following addition makes sense. What a random problem to try to solve. Um, there are two conditions. Each letter is assigned to a different digit, and the leading digits of the numbers are different from 0. Yeah, so the S and M, they must be different than 0. To solve these problems with constraints, the first step is to model the problem, to set up data structures and constraints that reflect the problem structure. In this problem, it is easy. Each digit is a variable, and the problem conditions become constraints on the variables. There are 8 different letters and therefore 8 variables. The second step is to define a one-argument procedure that implements this model. Figure 12.1 shows one way to define a procedure. The numbered statements have the following effects. Yeah, so this is essentially the English version of what is written here. So let's go. The solution solve is a record with one field for each different letter. That checks out. The fields of solve are integers of the domain 0 to 9. That checks out. The fields of solve are pairwise distinct. No two have the same value. Well, I'm believing the implementation of this is right, so this checks out. Since they are leading digits, the values of S, M, and M are not zero. Here they are. And then this is the equality that we're trying to find. And you have to do the multiplication by 10 and 100 and 1000. It's the same trick that we usually do for summing things. All digits satisfy this equation. The distribution strategy tries the letters according to the first fail strategy. This means that the strategy tries first the letter with the least number of possibilities, and with this letter it tries the least value first. So there we go. This computes and displays a list of all solutions. So here's an example of a solution. You can try it out to see that it actually does the thing. Modeling the problem. Modeling the problem is not always easy. Often there are many possible ways to represent the problem in terms of constraints. Yeah, so this is actually the thing that requires practice and expertise and understanding and being good at competitive programming in general.
It requires skills and knowledge, basically.
Constraints in distributed strategies. There are many constraints in distributed strategies to choose from. Which ones are best depends strongly on the problem. The first solution to a realistic problem is usually too inefficient. There are many techniques to improve it. Some possibilities are to take advantage of problem structure, as you're going to see later, to use redundant constraints, to use different distribution strategies, or to use the Explorer, which apparently is a GUI tool to see the tree.
We've seen an example of a redundant constraint already with the less than or equal to in the first example, right?
Well, I wouldn't call that redundant necessarily because this was done to make it to get the solution faster. So I wouldn't say it was redundant because the purpose was we want to get the solution faster, and we are
Well,
okay with the potential false negatives.
that's kind of the point, right?
Yeah, but if you care about the false negatives, then you have a problem.
Well, yes, in this case, because it's a rectangle problem, right? You actually don't care about the flipped solution,
Yeah.
so it's fine, but in general, you need to be careful.
Yeah, so then we go back to the palindrome problem that we solved on 921 section using relational programming that took 45 seconds. And this is the constraint programming version of that. And it takes slightly less than 2 seconds. And then if you notice that this thing is a multiple of 11, which again, expertise, practice, good at competitive programming, things like that, you will notice these
Domain,
things.
domain knowledge in this case, right?
Uh, I don't know if I would call that domain because the domain of this
Well,
is mathematics. So
this is a numeric problem, and this improvement is exploiting properties of number theory.
well, you are right, but usually when people use the phrase domain knowledge, they mean that you are reducing the scope. And the scope here is still like surprisingly big, number theory. But I guess you're right? You don't have to care about other areas of mathematics, just number theory. So it is domain knowledge in this case. But again, you have to know this beforehand. Then you can rewrite these things in this manner, take advantage of this. We can simplify and specify the problem differently. And then we go to this formulation here. A constraint-based formulation of a combinatorial problem can be much faster than a generate and test formulation. For palindrome and product, the constraint solution is more than 100 times faster than a naive solution, obviously. To make it fast, you have to take advantage of the problem structure. A little bit of smarts goes a long way. For a palindrome product, taking advantage of the solution being a multiple of 11 makes the program 5 times faster. A fast solution is not necessarily more complicated than a slow solution. Compare the slow and fast solutions to palindrome product. They are about equal in length and easy to understanding. I would disagree with that because looking at this from the first time, I would say, okay, how did you guys get those numbers exactly? And if nobody told me that, oh, it's because of the multiple of 11, I would be, oh, this doesn't make sense to me. So the easy of understanding is kind of like, okay, if you know that, then it's fine, but if you don't, then it's not easy. Performance can depend strongly on the exact problem formulation. Changing it a little bit can make it much faster, usually much slower. To write a good specification, you have to understand the operational meanings of the constraints as well as the logical meaning. The latter is enough for showing correctness, but the former is essential to get good performance. And finally for today, 12.3, more about basic constraints and computation spaces. A computation space collects together basic constraints and propagators. The basic constraints are a constraint store. The propagators are threads. A computation space is always created inside a parent space. It can see the constraints of its parent. In the figure, X is bound to a computation space that is created inside a top level space. So we're talking about this figure. So it's essentially like, I don't know, this reminded me of the scoping problem.
I mean, you are kind of implementing some scoping rule about when the binding of a logic variable is visible or not, depending on where you are, right?
Yeah, I would say so. Uh, okay. Um, basic constraints and propagators. Introduce basic constraints for finite domains as equations of the form x contains d, x is containing d, where d is a finite integer set. This partial information is stored to the store by this statement. The domain d is specified with a compact notation. Successive tells this thing restricts the domain of x to be the intersection of all of those d's, provided that the letter is non-empty. Telling the empty domain for a variable would result in an inconsistent store. So such tell must fail. And do you see why? Because the variable that is being described as uh, being member of an empty state doesn't make sense. So it would fail.
Well, yes, if it must belong to a set and the set is empty, absolutely no value can satisfy that, right?
Exactly. The basic constraint and that is simplified to the equivalent relation. The usual variable declaration does not tell explicitly the domain of a fresh variable. Its domain is implicit. It is a domain of rational trees. A rational tree is a non-partial value build with records and other basic values. Equality with partial values acts as a domain restriction. For instance, telling this thing restricts the domain of X to the rational trees that match the partial value this thing. I think they changed this in the new version. I don't remember seeing Z in there. A propagator is simply a thread that tells domain constraints to the space according to their semantics. Each time a variable's domain is changed in the store, the propagators that use the variable must be given a chance to execute so they can propagate new information to variables. Waiting for a domain change is a fine-grained variant of waiting for determinacy. A multi-set of propagators must have a concurrent declarative fashion because that makes controlled search effective. Yeah, they changed the text. I read
Oh,
more
did
than
they?
this thing.
What did they add, out of curiosity?
Okay, so let's see if I can pull this off. Oh, there's way more in 12.3.
I wonder if this is the case of just maybe they expanded the text, maybe they moved stuff from later to here. I don't know.
Wait. Well, let's just settle what's next for next section, and then I can try to search the statement that I was looking for about the distribution strategy and things like that. Because now I'm wondering if what I read is actually not in this PDF, and that's why I was
Uh,
already confused.
it might be, but it could be later because I know for a fact that at some point in this chapter we're going to see how to implement the relational model using the constraint-based model. And at that point you see, okay, here's how you implement the choice statement, which controls search, right?
Mm-hmm. Yeah, but there's way more text, man, in this 12.3. 12.3.1. And there's actually 12.3. Oh, I found it. Yeah, it's not in here. Okay, so in here we finish 12.3 with 12.3.1, and that's it. And then we go directly to 12.4. In here there is actually a 12.3.2,
Ah.
which says like the following. A search strategy defines how the search tree is explored, depth first or breadth first. A distribution strategy defines the shape and content of the search tree, how many alternatives exist at a node, and what constraint is added for each alternative.
No, that is still in the text, but it's in a different section. It got moved.
Yeah, but that's why I was emphasizing that the search strategy and the distribution strategy are very different. The
Yeah, I
search
was
is about
misremembering.
depth and breadth, and the distribution is about what's going to be the new constraint added to the bifurcation and how many alternatives exist at a node. That's what this is about. Okay, but it's good to know that they just rearranged it. Okay. Okay, anyway, so next time we're gonna do
Ah.
12.4 all the way to the end, I believe. To the end of 12.
Yeah, we should be. Yeah, we should be able to finish chapter 12.
Yeah. Where is the thing? Oh, here it is. Okay, so we're gonna finish 12. So we're gonna go all the way here. 22 pages, that's fine. And then after that, we're gonna do 13 plus the D, right? So these are like 7
Y-
pages, and the other one, 11.
Yeah, 13 is kind of large, but it's also a lot of detail, which we'll probably skim over.
Yeah, that's why there's so many pages, but we're gonna skim over that. Okay, anyway. So there we go. I'll finish the recording now.